It is my great pleasure to introduce our speaker today, Dr. Telesca from University of California, Los Angeles. He's currently a professor of biostatistics in there. Dr. Telesca received his bachelor degree from Bocconi University, and then he received his PhD in statistics from University of Washington in 2007, supervised by Dr. Lourdes in Norway. And then he spent 2 years at UT Anderson Cancer Center as a postdoctoral research fellow. Dr. Telesca's research interests include Bayesian multivariate analysis, functional data analysis, graphical models. He has done fantastic work in both theory and applications. A lot of his works are motivated by important applications in bioinformatics, nanoinformatics, and criminology. Dr. Telesca currently is a member of the California Nanosystems Institute and the UCLA Youngstown Comprehensive Cancer Center. So let's welcome our speaker today.
Thank you for the generous introduction, and thank you for dating the steps. Yeah, that way people can do the math. It's a good pleasure to be at A&M. Actually, I did a lot of time in Texas. That's how I like to put it. But I've never made it all the way to A&M. I spent some time in Austin, some time in Houston. So first time at A&M. Great to see a lot of old friends and a lot of faces that I usually only see on Zoom these days. So it's a bit jarring to see real people. But it's a pleasure to be here. So this is actually work that we've done in collaboration with some of my very attractive colleagues. The person that actually did most of the heavy lifting is Nicholas Marco. Nick is my PhD student, and he's kind of close to finishing. I'll be starting a postdoc at Duke in the summer. We'll see if we let him go. And Damla Shenturk, which is a colleague of mine in biostatistics. Damla is, of course, well known in the field of statistical applications in psychiatry and also functional data analysis. And then Shafali Jeste and Abigail Dickinson are two neuroscientists at UCLA Samuel Institute that actually carry out most of the studies that motivate some of this work. So just to give you a brief motivation, I'm not an expert in the actual technology, but I'll sort of give you my sort of poor man's understanding of brain imaging using electroencephalograms. The idea is quite simple. The idea is to actually sort of monitor the electrical activity, typically in the cortex and subcortex, using a simple set of electrodes that are placed on subjects. And there's different kinds of experiments that can be sort of set up in a brain imaging situation. Typically, the kind of studies we're interested in relate to the notion of functional brain imaging. So the idea of trying to understand, for example, how the brain responds to stimuli, or even how it acts in resting state as you look over multiple sort of subjects. So the area is truly quite expansive in terms of exactly how this technology is implemented and the kind of phenomenon you can actually record or actually image using electroencephalograms. They're very popular when it comes to neurodevelopmental studies, because typically the subjects are children, and the imaging technology associated with EEG is quite robust to applying it to a child, because it's robust to movement and distractions and things of that kind. So if you're familiar, for example, with other strategies like MRI or fMRI, those studies tend to be not particularly useful in the case where you're dealing with sort of small people trying to get them to do tasks or things of that kind. So we'll think about this kind of data, and the kind of data you get essentially is a set of multivariate time series associated with each one of these electrodes. And so the goal is to sort of try and think whether from these sort of high dimensional signals we can sort of discover something about differentiating elements between, say, individuals that have been sort of categorized in a rather rough manner in a clinical perspective as ASD, TD. ASD will stand for autism spectrum disorder children. TD will stand for typically developing children. Just to give you a quick idea of the kind of data that we'll consider. So there's many ways in which, of course, multivariate time series can be analyzed. The kind of focus for the study will be analysis of the spectral features of this time series. Essentially, we'll consider already the spectral density associated with the signals as our main object of interest. So this is a case where you do see multiple spectral densities for each electrode, or sometimes for regions of the brain, and over multiple subjects. The idea is that in neuroscience, typically the analysis of contributions to the sort of frequency range associated with these signals and sort of the relative magnitude of, say, these delta, gamma, alpha ranges of frequency tend to be associated with very well established patterns of neurocognitive behavior and also neurocognitive development. So it's going to be one of those cases where we can truly assign meaningful interpretation to features which are essentially purely mathematical. So this is just a snapshot of the data that we'll consider. And it's a snapshot of spectral densities considered around 10 hertz of frequencies. So this is known as the alpha range of frequencies. There's a debate into whether that alpha range or the exact range of these alpha frequencies, but we'll just take a window around this alpha range. And this is just a number of spectral densities or snapshots of that spectral density associated with multiple subjects, both typically developing and ASD children. The idea here is that we have children of in an age range between, I think, 2 and 8-year-olds. And the idea would be to sort of understand whether we can say something about this sort of different clinical categorizations of this group by simply looking at data. Yeah. So of course, at this stage, if this is your data set, you can think of all the analysis that we usually deploy. Yeah. So we can think of just doing functional regression, simple supervised learning, unsupervised learning. And for this particular application, we'll consider a notion of clustering or some generalization of clustering in this setting. In particular, what we'll try and do is think about clustering this data on a continuum. So the idea would be of thinking of this data as mixing continuously between underlying latent features, which may be of importance or may be more easily interpreted than the data themselves. So this is like my poor man's animation of that process, right? But the idea is that as I look at this particular data set, and if I think about clustering, of course, clustering is something you can do. Yeah, it's one of those beautiful mechanisms that you provide the input and you get the answer. Yeah, but the question here would be, well, is it really meaningful to adopt sort of or to think that there are truly 2 latent subpopulations in this picture, and that I can sort of pull them apart easily? Knee-jerk reaction, just looking at the data, probably not exactly. Yeah, but perhaps if we think about generalization of clustering as perhaps there's some sort of important features within these functions, typically the kind of feature, I'll give you a little preview, a little cheating preview, the kind of feature that we care about is this sort of peak in alpha range around 10 hertz, which typically is associated with neurotypical children. So neurotypical children at rest show a well-defined alpha peak around 10 hertz. And that peak becomes better defined with age, and it tends to move towards higher frequencies with age. So that's kind of what we know from a neuroscientific perspective. This is on neurotypical kids. For ASD kids, there's no real knowledge about what should be expected of this sort of alpha frequency range. And so the idea, of course, is that clustering itself may not be appropriate, but if we can think of sort of continuous mixtures over, say, multiple latent features, maybe we can make some progress in understanding the underlying patterns in this data. Please feel free to interrupt me or stop me or complain. I understand that I'm the only thing standing between you and lunch, yeah, but it's okay. So just to give you also a very, very high level perspective of the process, right? So the idea is that when we think about clustering, we're really thinking about the existence of sort of latent subpopulations, which are very well determined and perhaps identified in our data. And we think of clustering, if I were to think about this sort of latent matrix of allocations, we think of it as being an exclusive allocation, right? So subject 1 would be coming from subpopulation 1, subject 2 from subpopulation 3, and so on and so forth. And the idea there is that when I evaluate probabilities, if I were to have a probabilistic evaluation of membership to these clusters, I'm really thinking about uncertain membership to some of these populations. So of course, we're never really 100% sure that subject 1 comes from population 2, but I can quantify that uncertainty intended, and this is a bit of a nuance in interpretation, intended of uncertain membership to that particular subpopulation. A different view, which is popular, for example, in categorical data settings, is a view of the existence of multiple features rather than subpopulations, and having individual statistical units load onto one or multiple of these features. So the idea, the classical example would be if you're browsing on your Netflix, there will be a horror movie. There's also a comedy, or I can't think. I think my Netflix analogy stop here. But the idea is that these two things are not exactly completely different, right? But from an interpretational perspective, you're now thinking of uncertainty around this sort of allocation matrix as mixed membership rather than uncertain membership. So the idea that perhaps if I look at these underlying features, or if I look at my data, I can sort of think about sort of common underlying features in this data, latent components, and then think about whether I can ascertain how subjects load onto these features, if you like. So a lot of related concepts, right? So similar concepts, for example, come from a standard factor analysis or principal components analysis. But we'll see that we'll just give this perhaps an easier interpretation, or maybe more complicated. It's easier in my head, yeah, because I just made these slides. All right, so just to kind of give you a quick idea what we'll be working on. So as I was saying, this type of modeling is actually quite popular in categorical data analysis. If you're familiar with topic models and things of that kind, used a lot in natural language processing and stuff like that. The idea is that typically, if we go fully Bayes, we'll need to consider, for example, a sampling model, so a way in which we conceptualize how the data is generated. And then there's some work done on this allocation matrix. There's actually quite a bit out there, especially in the Bayesian parametric setting, because you have to think about some sort of discrete stochastic process that generates these underlying feature allocation matrices. So we'll actually forget about this altogether, because we won't really be bothering with a parametric treatment of these allocation components. And I don't know if I have a good justification for it. It just seemed easier to just not bother too much with this component, but actually think a bit more closely about the sampling model. Just because, as you can imagine, as we go into continuous data, just like in the case of regular mixture models, there's a lot of options there. Yeah, you can sort of dream up whatever sort of flexible configuration of what do you mean by cluster, what do you mean by a latent feature. Yeah, so we'll try and think a little bit more about interpretation of what we mean by continuous mixtures of fuzzy clustering or mixed membership models when your data is continuous. When your data is discrete, it's easy, and I'll tell you why, or easier. I hope your vision is good. So the idea here now is that if I start thinking about mixture models, the idea is super simple. So if I have the notion of standard model-based clustering, or if you like, if I think of my sampling model as being defined in relation to essentially a mixture distribution, the idea is that as soon as I think of a particular sampling model for subpopulation, say J, then I'll simply think of, say, Y coming from this convex combination of, say, J underlying distributions. Of course, the common representation is by considering sort of a latent representation of this picture. So if I think about my, rather than pi, I'll have for every observation, I'll have a ZI tilde, which I can barely see. I hope you guys can see it. So the ZI tilde is typically in 0, 1, in the sense that it's either 0 or 1, is an indicator of subject I, say, belonging to component K. And so typically I can represent then this, I can have a complete data representation of my mixture model in terms of basically indexing these densities or elevating them to a power of Cij. So what happens when we think about fuzzy clustering or mixed membership or partial membership. The literature tends to have sort of different related nomenclatures for some of these models. Well, a common strategy is to actually take these Zij in the complete data representation, which is just either 0 or 1, right? So this can only be 1 for one of the categories, and actually just plug in a value between 0 and 1. So rather than actually having an indicator function here, I'll have essentially a probability. So nothing too deep here. In fact, what happens is that if you actually use this particular representation, in many cases, you can actually work out nice properties of what the underlying distribution would be. So typically, for example, if you think about categorical data, what that would imply is something quite simple. It would simply be essentially continuous mixing over the categorical probabilities. Yeah. So it turns out that you can actually do that for you can do that for a number of distributions. In particular, for example, if you have distributions in the exponential family, what happens is that this particular representation, notice that here I'm using a proportionality constant here, because as soon as you change the Zij to be a probability rather than a 0 or 1, you have a normalizing constant there. And so that in principle could be a problem, right? But in reality, when you look at exponential families, the idea is that things do simplify quite a bit, because now your sampling distribution is simply defined in terms of it's still a member of the same exponential family, and the only thing you're doing is actually doing convex combination of the natural parameters of this family. So of course, easy enough if you have categorical data. In continuous cases or in the general case, I think one may have to think a bit harder about what actually happens, or what does it mean to actually have convex combination of natural parameters. And this case is particularly evident in the simplest case, and this is the case that is related to what we'll be doing, which is the case of Gaussian distributions. So imagine, so here I have basically different configurations of my allocation probabilities. Yeah, so whether you have sort of probabilities that come with a very high concentration along the main features, or that mix a bit more heavily between features. The idea is that here I have sort of 3 pure mixture components, and I think of my data as being generated using this underlying mixture of natural parameterization. So the idea is that I have a convex combination of the mean scaled by the concentration matrix, and then a convex combination of the concentration matrix. And so this is the kind of realizations you get. That's fine, but it's perhaps a bit counterintuitive, yeah, at least in some settings. The idea is that it's most evident, for example, if I think about the case of a very well-defined sort of mixture allocation in terms of typically data moving between, say, 2 but not 3 of the underlying features. And typically here what happens is that the data will organize itself along almost this manifold determined by the underlying directions of these hyperellipsoids of variation. Of course, yeah, I only have 2 dimensions, yeah. So perhaps not immediately intuitive, because if I were to look at realizations in this area, for example, I would think of it as realizations that are somewhat defined as in between the blue and the red cluster. I don't know if that's really natural. Fine, it's something we can certainly define analytically, yeah, but perhaps from an interpretational perspective, it may be somewhat unnatural. So what we'll try and do is actually think a bit more about this particular representation, and actually we'll use an alternative. And then I'll try and translate that representation to functional data. So the step is really straightforward. Or that's what I tell my student, yeah, you have to do all the work. So. All right, so this is kind of the picture that we have in mind. So this is the original representation, a typical representation that is often goes under the name of partial membership models. Again, what I think as a somewhat unnatural notion of in between 2 features, right? It's just what sort of the underlying definition works. And so we'll actually think about defining realizations that actually would look more like the picture to your right. So this is actually familiar in some subsets of the literature that identify this properly as mixed membership models. And so in this case, what we'll see is that we have the same sort of pure mixture components, but we'll think about realizations that go in between these mixture components as perhaps realizing more naturally exactly in between within our understanding of, for example, a Euclidean space. So we'll see that actually the idea is not too difficult to develop. Yeah. So of course now the question is we want to translate some of the idea to the case of our EEG data already processed to determine sort of the spectral features or spectral densities within a range of interest. Yeah. Nothing stops us from examining the entire spectral density, but in this particular application, which is the study of the brain at rest, this particular range of frequencies is of interest or more easily interpreted for neurodevelopmental studies. And so we'll actually try and think of these data now as being functional data. So if you're not familiar with functional data, then, there's many ways to think about functional data, but perhaps a natural way to think of it is basically just you're thinking of these sort of realizations as realized paths from a stochastic process. And that stochastic process is often sort of defined in the functional space. We'll see that from a Bayesian perspective, we'll just operate in much more precise settings. Yeah, so we'll operate within the Gaussian process framework, which is, makes some of the traditional functional data analysis people a bit nervous. Yeah, but here it seems friendly territory. Yeah. All right. So the idea, of course, is the idea, or at least this is my sort of snapshot of what FDA is all about. By FDA, I mean functional data analysis, not the regulatory agency. But the idea here is to say, well, we'll think about methods in general that sort of focus on the analysis of this sort of realized path from a stochastic process. There's all sorts of principles that one may have to adhere to. But the idea is that I'm thinking now of my data typically as being some sort of smooth function phi of t. It's sort of natural to think of t as a function over time, but t can really be anything, right? So in our case, t will be a range of frequencies, and we'll see that then in multidimensional cases will be a range of frequencies projected over a spatial domain because you have imaging of the entire brain. But so in principle, you can think of it as a simple structure where you have some sort of phi of t, which is typically a Gaussian process plus some error process. This Gaussian process is often characterized by a mean and a covariance. And so typically, I think within a lot of the literature, the work on Gaussian processes relies upon a much harder problem, the problem of actually obtaining typically one realization of the process or observing one realization of the process, or maybe some related realizations, but not exactly independent replications from the process. And so in the case of a functional data analysis, you have the luxury of observing independent replications from this process. And so typically the idea is that you actually move away from defining or from thinking about properties of covariance functions, and you simply think of estimating these covariance functions from the data. So you try and be somewhat more data-driven in the estimation of these covariance functions. So typically, for example, if you only have the luxury, if you only have the curse of observing one realization, the best you can hope for is sometimes the estimation of parameters in a parameterized covariance surface. In functional data analysis, you can do a bit more. You can sort of try and think about whether you can estimate that covariance function. If you think about it, yeah, if I were to discretize my data, everything is not very Gaussian, we can certainly estimate a covariance matrix. Yeah, so we'll just actually think about how this can be done in a more regular setting. In fact, we won't spend a whole lot of time on this. Yeah, so there's actually quite a bit of literature, but I'll tell you a bit about it when we get into our modeling strategy. So when we think about clustering in functional data analysis, again, this is my translation to pure probabilistic characterization of clustering in terms of mixed redistributions. One can think of it in a more sort of abstract, or if you like, general setting. But if I were to think about this probabilistically, well, I think now of clustering functional data as basically mixtures of Gaussian processes. And so we're sort of back more or less to the same idea that we had before, except now we're working with realization of a Gaussian process rather than a multivariate vector. So, so the step, of course, between this correspondence and the idea of generalizing this to mixed membership models for continuous data is straightforward. I will just actually think of it as mixing over functions, if you like. So again, we have a simple process here. we'll call it mixed membership functions, where these FKs are my sort of latent features, which are defined as being realizations of a Gaussian process. So I have K of these Gaussian processes, right? So these are my sort of latent processes that define my distribution over functions. And so I'm going to think of each realization as being simply equivalent distribution to this convex combination of K latent Gaussian processes. So it's as simple as that, not too different from what we have sort of built intuitively in the regular case. The only thing that we'll actually think about more carefully is what it means to actually define convex combination of GPs, because typically what will happen is that as you consider now this sort of continuous mixing, you end up with covariance structures which are kind of restrictive. So essentially, the covariance structures will be sort of not exactly convex combinations of the original covariance, but they will be combinations involving these probabilities, these ZIKs squared. And so they will typically be reduced to be smaller if you have mixing between two underlying processes. So we'll just, the way to fix this is to actually think about these K Gaussian processes as not being independent, but as being sort of related to each other. So just a small deviation. So this is just a quick, again, my poor man's animation, what we think about. The idea is that if I think about finite mixture models for functional data, ideally, right? So if I had to have the ideal data set, that's the kind of realizations that I would think about. So two GPs and then realizations around this Gaussian process. Whereas typically, of course, when you look at data in functional brain imaging, you're lucky if you see anything sort of that moves between two underlying features. So again, it's a bit of an abstract construct, right? So it's truly, I always tell my students, yeah, I don't want to hatch any of this findings in stone. Yeah, it's really an unsupervised look at a set of data that may or may not be useful. Yeah, so we'll see whether it is. I'll let you decide whether it is useful. There's quite a bit of related work in the literature. So, for example, if you look into the Bayesian parametrics literature, there's some work by Sonia Petrone and Michele Guindani and Alan Gelfand that actually think about this notion of partial membership, but more in terms of subsetting the domain of these realizations in functional data. So there's some relation there, but not exactly the same. Something that is perhaps more related is the work by Suarez and Ghoshal that actually think about continuous or mixing partially over sort of different levels of resolution in a wavelet setting. So again, you're still thinking about your observed datum not being easily allocated to one particular class, but perhaps arising from these continuous mixtures over several latent features. All right, so what does this process look like? Well, the good news is that this process actually is super straightforward to then characterize as its own Gaussian process, right? So the idea is that now, from an interpretation perspective, we have the advantage, for example, that the mean structure is not the convex combination of the mean scaled by the concentration matrix, but it's just a convex combination of means. And the covariance structure is straightforward. So it's just basically this quadratic combination. I don't know how to define this. So basically, it's a combination of the original covariances of these latent GPs multiplied by the Z's squared, plus the cross-covariance components. So these cross-covariance components comes from the fact of assuming these latent Gaussian processes as being possibly related. And they actually are quite useful, right? Because they allow for a full representation of all the different covariance structures that I may actually observe in the data. What happens, of course, is that, of course, now you have to worry about several Gaussian processes. I have K processes for the mean. I have K covariance functions, and of course, K times K minus 1 over 2 cross-covariance functions. We are typically not too worried about dimensionality here because in most applications, you don't really hope for too many underlying features, yeah. But it's something to start considering. And so what we'll do next is actually think about how to characterize perhaps the sort of underlying related KGPs using essentially just a sophistication of spectral decompositions, essentially, and then actually think about what's going to be their sort of their structure in terms of sort of parameterizing all of these covariance functions and mean functions and so on and so forth. All right, so so the joint representation of KGPs, there's of course many ways of doing it, but an easy way to do so is to actually kind of think about a simple KL or Kernan-Loew representation of these K Gaussian processes. The idea there is quite simple. You essentially, it's almost like vectorizing this sort of multivariate vectors of realizations, and then providing a basis representation of these related vectors. Here, notice that the basis representation involves, in our implementation, involves two steps. One step is essentially expanding with respect to a known basis system. This may or may not be necessary. One can simply actually think of these functions as being GPs themselves. But the key here is to actually think of these underlying bases as being learned from the data, right? So you're actually thinking of this sort of underlying basis system as coming from the data. Of course, if we discretize, we only have Kp in the saturated model. So P is the number of basis functions and K is the number of features. And typically what will happen is that we actually can go much lower than Kp, right? Because typically if we have functional data, we really think of possibly explaining most of the variance, with only a few sort of eigencomponents, if you like, in this sort of multivariate process. Of course, the idea here of using sort of an initial set of basis functions is just sort of eminently practical. Yeah, it just makes computation much easier. And if you like, it has the feature of actually allowing you to change the basis system if you think that it's sort of warranted in different applications. So if I think now about what happens is that typically, rather than going all the way to K times P eigencomponents, I'll stop at M, which is typically much less than K times P. And we'll see how we do this sort of adaptively. Yeah? So we'll actually think of this as a regularized estimation problem. So we'll have M large enough to sort of span the entire total variation in the observed data and sort of regularize the process through multiplicity gamma processes. So we'll explain this quickly. But the idea is that, of course, if you were to go naive, things can become unyieldy pretty quickly, right? Because you'll have K features times P basis functions times M underlying component. Sorry, I should say this is sort of our reduction in dimension. If you go with a naive representation, you have K squared times P squared set of parameters, which can become unwieldy because typically of P. Yeah, so P is the number of basis functions that typically mimics the sort of grid refinement observation of your functional data. So typically, if you have highly sampled processes, so if you can, and this is the case, for example, in EEG, where you almost obtain an analog read into your data, then P can be quite large. And so the idea is that this reduction is certainly useful, even though it's not really the focus of this idea. Yeah, so the focus of this idea is to really kind of think about modeling or representing sort of K-related GPs in terms of this sort of regularization process involving eigencomponents, or if you like, eigenbases, which are defined by these phi im terms times beta t. So this is just another poor man's picture of what I'm thinking of when I think about relatant GPs and how they can affect essentially the realizations in sort of continuous mixtures between the two latent features. So again, here I have sort of two pure mixture components, which are the sort of the extremes, and then data that can be realized in between. And when I think about covariance functions in functional data, covariance functions essentially determine the sort of heterogeneity that I can observe within a particular GP. And so, of course, I would like the flexibility to have maybe more stringent or more general covariance surfaces. So the idea is that, of course, allowing for these cross covariances, even though it comes at a cost of having to model them all it provides a much broader expressivity, if you like, of the sampling model associated with these processes. All right. The good news is that the final dimensional margins we're back to Gaussian territory. Yeah. So it's a graduate student dream come true. Everything is conjugate, and we can operate with our standard technology. Yeah. Until of course Nick told me that he had to do a lot of tempering and stuff like that. But in principle, right? I can even write down a likelihood. Yeah. So I'm fairly happy so far, yeah, for this general setting. So the idea, of course, is that seriousness, that the margins are available in closed form, which is great both for interpretation and for computation. And so here comes this could be another talk, yeah. So prior distributions in this case. If you think about it, we need priors on a number of things, right? And the most critical aspects of these priors are probably related to the covariance functions, or if you like, what we translated in terms of this sort of eigenbasis. And so there you have a bit of a problem if you go from a Bayesian perspective, because you certainly don't want to operate within the convention of mutually orthogonal basis, or you might, yeah, if you're mad enough, you're David Dunson, but it becomes a rather difficult sampling problem, and typically, if you wanted to actually assume mutual orthogonality, you may end up dealing with now a very deep computational problem of trying to mix well over these very constrained spaces. So what we'll do is just ignore it altogether, but what we'll maintain is this notion of regularization through a multiplicative gamma process. The idea is to actually parameterize the variance components of these underlying basis coefficients to be related to each other in terms of this process. So this is a common process that is used typically in factor analysis or even in functional data analysis. And so in expectation, what happens is that as you add more and more eigencomponents, in expectation, this prior will shrink the magnitude of that variance component. And so you can actually now think of it as a regularization process, where of course adaptive estimation comes from essentially integrating over this sort of regularization process that kind of shrinks continuously the magnitude of our variance parameters as I add more and more variance components. So if you think about this from even a principal components analysis perspective, right? So by construction there, you have that the first principal component explains most of the variance, and God willing, then things kind of go down and explain less and less of the variance. So here we're not really enforcing it, but we're encouraging that sort of regularization by defining priors that sort of penalize more and more as you add more and more eigenstructures. This is a bit of a contentious point, especially with our referees. Whenever you have theory and mixture distributions, the two things tend to not gel too well. It's quite difficult to actually prove much about what would be sort of the properties of an inferential procedure that kind of works with these highly flexible models. And the problem essentially is related to the fact that nothing is truly identifiable. Yeah, we can post-process, we can constrain, but it's very hard to say, okay, I can give you simple identifiability conditions for which there exists a unique maximum a posteriori, for example. So the only theory you could actually develop is just for the case of imagine that a supernatural entity had given me all of the allocation parameters, so the allocation truths. So in that case, we kind of know that the model is flexible enough to ensure consistency in the posterior distribution. This is truly partial, right? Because at the end of the day, understanding and learning about these allocation parameters is important, but we couldn't quite get too far, or at least that's something that Nick can do on his own time. Yeah, I'm done with it. Computation again, at least within this setting, within the setting of functional brain imaging, typically it's one of those cases where you have valuable data but not a lot of data. And so dimensionality is not a huge problem. So we can still operate within simulation-based inference. So basically Markov chain Monte Carlo. Everything is more or less straightforward because we are working within the Gaussian framework, except of course, because of the continuous allocation structure. So we're not really operating within a proper Gaussian framework. You do need a bit of sophistication in terms of tempering some of these samplers to make sure you mix well and you don't get stuck in strange local configurations. These models are quite flexible, so it's quite easy to sort of get stuck into local modes of the posterior surface, which are not exactly ideal or optimal. So there's quite a bit of sophistication in the computation, but truly nothing out of the basic ordinary realm of Markov chain Monte Carlo. So that's just some quick simulations. I'll probably go through this quickly. The idea is that we didn't have a lot of theory for the allocation parameters, but it seems as though with increasing sample size, we still have some learning over these allocation parameters Z's. That's the most important thing. Clearly, yeah, if you can't learn anything about the mean and the covariance, then you're in trouble, yeah. But the Z's are important. So we're sort of reassured that, at least in simple cases. So this is a very simple simulation with 2 underlying features. Actually, I think 3 underlying features, and sort of generating essentially from something that is very similar to the model. Yeah. Something a bit more pernicious is actually understanding the number of underlying features. So here we are operating in what Bayesian non-parametricians would say it's anathema. Yeah. So I'm fixing K and then operating, rather than having a stochastic process over K. In principle, you can do it, yeah, but in practice, good luck. The idea, of course, here is if you actually condition upon K, then you have to sort of select K somehow. And the selection doesn't seem, so we kind of thought about multiple information criteria. And I won't get into the controversies about how to define, for example, a DIC or a BIC when you have this sort of high dimensional models. But in their straightforward interpretation, what happens is that these criteria applied in the nominal fashion. So the idea of just choosing the model that minimizes, for example, a DIC or maximizes a BIC tends to overshoot. So tends to actually include more features than what you actually use to generate the data. What we found actually works much better is your undergraduate statistics clustering algorithm of saying, oh, just look at the elbow point in this sort of information trajectories and pick that as your number of features. Again, we don't really have a lot of a very good understanding or theory around optimal selection of the number of underlying features, but that's still a contentious issue, especially in Bayesian parametrics. Yeah, so if you want to embarrass a Bayesian parametrician, ask them, can you estimate the number of clusters consistently? I don't know. Yeah. Christian Robert has had a talk recently, but I wasn't there, so I've seen the talk. It's not easy, but in a way, at least empirically, it seems that reasonable use of standard information criteria still gives you reasonable answers. In this case, because these models are quite flexible, I think it's always useful to be very parsimonious. So if you're undecided between, say, 2 and 3 features, yeah, 2 seems to be a good way to go. All right, so just back to the data. I promised you some nice interpretation. I told my student that it was too good to be true. He assures me it's true. But so this is the kind of data that we'll consider. So EEG data. This is a study of neurodevelopmental disorder. So we'll try and compare autism spectrum children with typically developing children. There's a set of ages that we're considering. But without further ado, so this is kind of the idea. So the idea is to say, well, can I learn any sort of discriminant feature that sort of pulls apart TD and AST kids? But for typically developing children, we kind of know what to expect. We know that they should develop a very nice and prominent alpha peak around the 10 frequency range. For autism spectrum disorder kids, there's no established literature on the subject. So I'll because in the interest of time, I'll skip this sort of standard analysis, but I'll keep the clustering. So the idea here would be, well, why don't you just do clustering, right? So if I do clustering, the number of clusters supported, again, I think because the data is really quite all over the place, there really isn't, or at least we couldn't really identify a notion of well-defined underlying subpopulations. Clustering, functional clustering, provides these 4 clusters, which as you can see, are sort of just smearing over the entire variability of the data, right? So you can't, I wouldn't necessarily interpret this sort of cluster means. They just basically pick up the phase variation around this sort of ranges of frequencies where different subjects will develop the alpha peak as slightly different frequencies. So not particularly interpretable. We actually pushed this over even to 2 clusters, and we still have very ambiguous representations of these subpopulations. A feature allocation model actually identifies these 2 underlying features. So we went through the step of selecting the number of features, considering basis expansion. In this case, it was just PE splines, and then these are basically the 2 feature means. The 2 feature means are actually, that's why I'm saying it's almost too good to be true, because the first feature essentially defines what neuroscientists kind of label as the 1/f trajectory. This is basically an underlying expectation of high frequency explaining less and less of the underlying EEG signal. And then the second feature, again, almost too good to be true, seems to be exactly sort of that alpha peak element that we expect to manifest in typically developing children. We can go deeper into analyzing the covariance structure, but somebody may actually stop me right here and kick me out of the room, so we'll just skip this. What's more interesting is, for example, thinking about if I were to now stratify by typically developing and autism spectrum disorder children, I can analyze the distribution of the sort of allocation parameter Z. So remember the first feature, actually I may have relabeled this, yeah, but the first feature was, the first feature was characterized by my 1/f pattern, so nothing particularly well defined. And the second feature kind of quantifies, if you like, the sort of appearance of an alpha peak in the frequency range around 10 Hertz. And so when I look at typically developing kids, what happens is that, of course, you have a range of observations, but most of them tend to have a good loading onto this particular underlying alpha peak feature. And what we see for AST is actually confirming what's in the literature. There's no real consensus in terms of exactly what to expect. These individuals are truly all over the place, and it's almost like a uniform draw from a distribution between 0 and 1. And so, of course, here now there's a question of is there something else that can explain, for example, this underlying spectrum? ASD is a bit like saying you have cancer, right? What kind of cancer? It's there's a whole underlying set of conditions which may be kind of defined a bit more carefully, but certainly difficult in the setting of neurocognitive or neurodevelopmental disorders. All right, so we operated in the same domain, looking at the entirety of the imaging. So the idea of looking at the entire set of electrodes, if you like. So we find sort of fairly robust results. So I'll just summarize quickly some of the points. So the idea is that often in sort of, especially in neuroimaging, but a lot of times in biomedical applications, this underlying notion of there exist K underlying subpopulations, and I'd like to quantify a certain membership to these populations, may actually not be immediately appropriate or easily interpreted. Again, here we're thinking about very flexible models. So the fact that you can actually represent the data with these underlying models doesn't mean that then the interpretation is warranted. And so we think that this sort of understanding more sort of mixed membership in the continuous data framework or mixed data framework could be quite useful in bioX applications. Our representation of these sort of related GPEs using multivariate KL representations kind of allows you to do regularized estimation, because we are dealing with sort of typically smooth realizations in the stochastic processes. At the same time, sort of mimic a lot of interesting literature that is available in sort of standard functional data analysis without worrying too much about, defining complicated process priors over these covariant structures. Of course, a lot of work is needed both on the theory of, for example, selecting number of features. Identifiability is not an issue. There's a whole new chapter to this in terms of then how to take the posterior samples and rescale them so that we can actually find a conventional identified representation of these allocation structures. It's very easy if you have few features. It becomes computationally challenging if you have a lot of features. So we won't talk about this today. And then thank you for paying your taxes and a few manuscript and software that you guys can use to play around or find bugs, please. Yeah, if you do, let me know.
Thanks, Tom. So I had a question about this data. You talked a lot about the speed, and I assume you're not using any of those models.
Yes.
The peak obviously is shifted. So have you tried to do some kind of integration of the data for the peak?
I know nothing about registration. I'm kidding. I'm kidding. This is so actually you nail it right on the head. So the idea actually, if we go back to the covariance functions, yeah. So here where you see, for example, this is the covariance structure associated with the latent GP that picks up the peak. What you see here is essentially that there's a lot of phase variability, right? So you're perfectly right. So ideally, we would like to include sort of phase variation within this process. That's something that another student is working on. And of course, the other idea is to actually possibly use covariates to sort of explain more of these sources of variability. So that's of course another good another extension of Nick's paper. Yeah, so age and both age and clinical designation, right, could come in easily as covariates that explain different behavior in these settings. Yes.
So I have a question about the interpretation of that latent variables. So let's say if you use the Netflix example you brought up at the beginning, say if the movie is both drama and horror movie. So ideally, we may want the Z to be, for these two categories to be both close to 1, as opposed to splitting the mass half and half. You have the constraint of Z lies on this simplex, half out of 1. So I guess once you get estimates from data set, how do you actually interpret those?
So the idea there is, you're right. So the idea, if I think about, for example, categorical data, I can almost think of each if you have multiple categories, right? I can almost think about Z mixing multiple categories differently. And I think that's often the case in topic models where you have Z's which are actually two-dimensional for every datum, right? In functional data, you often think of the function itself as your datum. So you would think, so the way in which we interpret it is just the entire function mapping continuously between two underlying features. A related idea would be, for example, to look at subdomains of the functional evaluation and possibly have different mixing in that subdomain. That becomes, of course, challenging. Yeah, I think only Michael and Sonia were mad enough to do something like that.
Any other?
Just one, it's a really nice talk. In terms of, and I think it's related to the discussion in terms of the variability, right? So it could be due to the mixed membership thing that's kind of right here. It could just be kind of natural variability around the clustering. So I don't know if that's taken care of here in some way, but can that be brought into the framework you have?
You mean the phase variability? Or
right, it could be phase variability or any kind of additional variability in this unobserved.
Yeah, so there's two issues. One issue is we're working with Gaussian processes, we're operating in the Euclidean metric, which may not be the best metric and if you're working with densities, for example. But I think a lot of flexible variability in amplitude is taken care of. These models are almost too flexible, yeah. But variability in phase is pernicious because then your understanding of these underlying features may be sort of like smearing over all these. In this case, that's why I was telling my student that this is too good to be true. So hopefully it's true. In this case, because of this sort of weird property of this mixed membership, that they kind of identify the extremal features, it's the problem is a bit alleviated, but we didn't really study it too carefully. But I think certainly including all of these sources would be useful, at least to understand, how this model, how these results stand to, for example, allowing for extra sources of variability in these processes.
Your computation, were you using the spectrum or not?
We're using it on the spectrum. It's not ideal. It's not ideal. Yeah, the log of the spectrum, unfortunately, seemed to destroy the entirety of this sort of peak alpha features. That's why I'm thinking, probably we should consider different sort of metric spaces, to work on.
So I guess it's.
Yes, I can think of so you didn't bring your own thumb drive because I will take it.